Uh, Good afternoon. Welcome for today's lecture from IRS, Dehradun, the outreach program. And today's lecture is on remote sensing observation of aerosols. So you very well know that the atmosphere consists of permanent gases, trace gases, and variable gases. So permanent gases consist of nitrogen, oxygen, and argon in different proportions, which are nearly constant. Trace gases, on the other hand, are in traces amount like carbon dioxide, methane, ozone, neon, helium, krypton, and there are variable components, that is aerosol and water vapor. Aerosols are different particulates in the atmosphere, and they are highly spatial and temporal. They have different variability, and they interact with the electromagnetic radiations in the atmosphere. Now, we see what is air pollution. So these are the airborne particulates which are there in the atmosphere, and the concentration of which the endangered the health of the well-being of different organisms on the earth. The aerosols is a class of particulates in the atmosphere. They have different sizes, and they are defined by different sizes from 0.001 micron to 100 microns. As you very well see that the aerosols, different sizes like smoke, smog, fumes, dust. So depending on whether it is a fine particle or coarse particle, depending on the diameter, they are classified as different names. But these are under the class of aerosols. Now aerosols are the particulates in the gaseous medium, and these primary pollutants consist of the particulate matter whose sizes are less than 10 micron in diameter, and particulate matter whose diameter is less than 2.5. So these are the fine mode particles, and these are the coarse mode particles. Now the sources of the aerosols, these are natural sources as well as the anthropogenic sources. The natural sources are like mineral dust, then the forest smoke, sea salt. Of course, sea salt is a large proportion. More than 72% are sea salt aerosols. Volcanic ash. Then the anthropogenic sources consist of the vehicular emissions, industrial emissions, and cooking activities. And if you see the percentages, oceans are large, more than 70% are in oceans. Hence, the aerosol generated from the oceans, that is the sea salt, are nearly 72%. Volcanic ash and dust consist of around 17%, and the aerosols coming from the biomass burning, that is a soot and smoke, consist of around 11%. So it means the natural portion is around 87% or 89%, and the anthropogenic is around 11%. So having said that, the proportion is less, but the impact of the anthropogenic aerosols on the environment or on the climate is very, very high. Now we consist of the different components in the air pollution. So like you must be knowing that there are particulate matter is aerosol. Particulate matter aerosol consists of different sizes, as we discussed in the previous slide. Fine mode particles or the coarse mode particles. Then the gases like SO2, NOx, carbon monoxide, lead, volatile organic carbon. So these are the that is the constituents of the air pollutants. Now air pollution. Now the particulate matter consists, as I said, PM10 or PM2.5. So PM10 is known as the inhalable particles, which can infiltrate the human respiratory system and causes lot many problems, lot many diseases, and it negatively impacts our human health. PM 2.5, on the other hand, is known as the respirable particles, and it can penetrate further, not only from the respiratory tract, but also it can enter our lungs and our blood tissues. The size, the mass, and the concentration of PM 2.5 or PM, they directly are related to causing the adverse health impacts on humans. So these particles can originate, as I said, from a variety of sources, from natural sources as well as anthropogenic sources. And most of the fine particles, that is PM 2.5, are originating from the anthropogenic sources. That is the human activities, like for example, the vehicular pollution, the power plants, refineries, industries, different biomass burnings, firewood burnings, residue burning, and etc. Now, why do we care about air pollution? Because we know that, as we have discussed, that it is creating adverse impact on the human health. So we are concerned about it. So the large emissions of aerosol particulate matter will cause adverse health impact on the humans. Also in the atmosphere, it reduces the visibility, and it causes many economic and other transportation losses. It dissolves in the oceans and causing changes in the pH value of the ocean. That is, it is becoming more acidic, and hence there is an adverse impact on the aquatic species, and hence the ocean fertilizers also changes. In the atmosphere, it reacts. It reacts with the different particulates, and it changes with the atmospheric chemistry. Cloud formation, because more clouds, more seeds have more clouds, and then that's why lot many aerosols are helping to form the clouds, and more cloud means a lot of albedo, less that is the more albedo, more amount of more sunlight reflection from the clouds, and less amount of solar radiation reaching on the ground. So there is a change in the radiation balance, and hence this will also impact on the climate forcing. So as we have seen that it adversely impacts the IPCC reports also see that there is a negative impact over the atmosphere. So the greenhouse gases leads to the warming effect, whereas the aerosols are having a cooling effect. So you see the negative is the cooling effect, and but the scientific community proved that many of the aerosols, some part of the aerosol causes the scattering, that is the cooling effect, and other aerosol particulate absorbs and it causes the warming effect. Like black carbon soot, they absorb solar radiations and causes the warming effect. Now also the feedback of aerosol, because aerosol also affects many of the processes, and particularly if we talk about the monsoon. So there are many research going on the monsoon, whether it has a positive impact on the monsoon or negative impact. So there is a we are not sure how it behaves. So somewhere it helps because of its nature. So it helps to propagate or advance the monsoon, but somewhere it also helps to decrease the monsoon. So there are regional and global climate models to better understand it, and lot many research is going on this. So more, as we know that more of the aerosol that are emitted in the atmosphere, so lot many cloud condensation nuclei are there in the atmosphere, and which increases the cloud droplets, and hence the it will help the more rainfall and hence good monsoon. But on the other hand, increase of aerosol also causes there is the more reflection in the at the top of the atmosphere. So it means that there is a dimming of the solar radiation at the surface. Hence, there is a decrease in the evapotranspiration or evaporation, and it means that the less amount of rainfall. So there will be a negative impact on the rainfall system. Now, coming to the properties, as I said, that the aerosols are differ in different sizes. So they are typically classified in 3 sizes, like for example the nuclearization mode, that is what we say is that the acting mode. First of all, the Atkin mode, that is the fine particles, that is 0.02 to 0.01 micron, and it means that they are resulting from the combustion process and gas to conversion ratio. Accumulation mode. In the accumulation mode, the diameter is between 0.1 to 1 micron, and these are coagulated. So Atkin particles coagulate together and form the accumulation mode. So the Atkin particles or the accumulation mode particles, they are called as a fine mode particles. Now, coarse mode particles, they are larger in diameter, that is more than 1 microns, and they are formed from the mechanical process like the wind blown dust, etc. Now, the optical properties. Now, in the optical properties, we say the aerosol optical depth. Now, aerosol optical depth, such as the scattering and absorption of the solar radiation happens, and which dependent on the wavelength, and which is intrinsic to the aerosol radiative forcing. Now, some of the this is one of the aerosol optical properties, that is aerosol optical depth. It means that how much of the fraction of the scattered radiation is absorbed or scattered on its path through a medium. It means when the solar radiation reaches in the atmosphere from the sun, how much particles in the atmosphere scatter or absorb, and how much amount of radiation reaches on the ground. So it determines the fraction of it, and this is exponentially it decreases, and this depends on a factor which is known as the optical depth. And using this equation, we inversely calculate the optical depth in the atmosphere. So, for example, if aerosol optical depth is 0.2, it means it is fairly a clean atmosphere. And if the aerosol optical depth, that is the aerosol loading, is very high, it means the pollution level is very high, and it means that the less amount of solar radiation reaches on the ground. Now, when we talk about the satellites, now how do the satellites measure it? Now, this thing is that the satellite measures from a distance in the sky, and they provide the atmospheric column reflectances. So normally the satellites, they measure from 600 to 700 kilometers above the Earth's surface, and a single satellite has a different sensors. Different sensors means the cameras measuring in different wavelengths, and they see the reflected solar radiation from the Earth's surface. Now, the solar radiation from the sun is reflected from the Earth's surface, and it travels through the atmosphere. So what happens is the radiation is either reflected or absorbed from the atmospheric particulates, and the satellite measures both of these, that is the reflected and emitted energy from the particulates, and this energy in a different measures in a different spectrum in the different cameras on board on the satellite. And then depending on the algorithm, what we do is we subtract the surface reflectance from the total reflectance, and we get the reflectance or the emitter from the atmospheric constituents. And from this, we try to estimate the aerosol optical depth, like we discussed here, in the last slide. Aerosol optical depth, that is the fraction of that is the amount that is scattered from the atmospheric particulates. There are different sensors on board the satellite platform, which are used to study the atmospheric constituents, like for example aerosol optical depth. And in that we use different algorithms, but the basic data is from the reflectance data in the visible channels. This is MODIS, that is the moderate resolution imaging spectrometer. In this there are 36 bands from the visible to thermal infrared bands, and we use the visible and near infrared bands to estimate the aerosol optical depth. So they come out with the different products, they depending on the standard algorithms. The MODIS come out, or they give the different products on at different scales and at different resolutions, not only on the land, ocean, but also on the atmosphere. So aerosol product is one such product, which has a definite algorithm, and which uses the spectral visible and infrared channels of the MODIS bands. So this is one such glimpses of this is the algorithm name, dark target and deep blue. For example, whether one wants to have aerosol loading over the ocean surface or over brighter or the land surface. So different algorithms are used, and also the clubbed algorithm. So dark target and deep blue also is used, both. For example, a scene has a ocean as well as land, so such integrated algorithm is also used. Multi-angle imaging spectrometer, MISR. This views in different spectral bands from visible to near infrared, and the beauty of it is it views in 9 different angles. So you get because different path lengths, because it has to travel, it has to interact in the atmosphere by different angles, and so your path length will be different, and hence it abstracts or it estimates the aerosol loading differently and accurately. Also, it tries to estimate the aerosol types, that is the which sizes, depending on the different sizes, whether the not only it is a integrated loading, but also whether the particulates are in a fine mode or in a coarser mode. Another sensor, it is the visible infrared imaging radiometer suite, that is VIIRS. So this is on board the Xiaomi NPP and was launched in 2011. So it has 22 channels of different resolutions, which are listed here. So 16 channels are in moderate channels, which are 750 meter resolution. 5 bands are in 375 meter resolution, and one is a panchromatic band, 750 meter. And they come out with the different products, and aerosol optical depth or aerosol product is one such product, which is defined by the same algorithm as defined in the MODIS algorithm. The MOPIT, measurement of pollution in the troposphere. So MOPIT is a 8-channel gas correlation radiometer, and it measures basically the carbon monoxide and methane, particularly gases, trace gases in the atmosphere. And for this, the 4.7 micrometer channel and 2.2 and 2.3 micrometer channel is used to measure the strong and weak absorption bands of the carbon monoxide. And for methane, around 2.2 channel is used as a absorption channel. And from the absorption channel, the concentration of particular trace gas is measured. This is another sensor. Tropomi is the sensor, and Sentinel 5P is satellite. So the tropospheric monitoring instrument, Tropomi, it was launched in 2017. It has a very narrow spectral bands, a very large number of spectral bands in this broad range of spectral ranges, and it senses in a very high resolution, that is around 7 into 7 square kilometer. Now the beauty of it is it measures not only different gases but also the aerosols. So from tropospheric ozone, nitrogen dioxide, CO, SO2, methane, and also the aerosol. Now another mission, Sentinel-3 mission. So basically it is an ocean force focused over the ocean parameters, but in that these channels, the visible and near field channels, are also used to estimate the aerosol optical depth. The ozone monitoring instrument, which is also known as an OMI. Now OMI is another view which measures not only pollutants, that is the trace gases of ozone, NO2, SO2, but also the aerosols. So this is at a resolution of 13 into 25 kilometers. So these are all the Earth observation satellites. Now this is a geostationary satellite. This is an Korean satellite. This is COMSAT 2B is a satellite, and this is geostationary environmental monitoring spectrometer is a sensor. So it's launched in 2020, and it measures large many trace gases apart from the aerosol optical depth. GOSAT is a Japanese satellite. This is the greenhouse gas observing satellite, and it was launched in 2018. So apart from different trace gases, it also measured the aerosol. So I'm showing you all the freely available open source satellite through which you can get the aerosol data or aerosol product. Calypso is a LiDAR, that is a cloud aerosol LiDAR infrared pathfinder satellite. So previously we are all passive sensors. It means it depends on the reflected solar radiations, and from this it devised by different algorithms to estimate the aerosol loading. Now here, this is a active sensor. You must be knowing about the active. You may be aware of the active and passive sensors. So there are two wavelengths, that is 532 nanometer and 1064 nanometer. So in this wavelength, the pulses are sent in the atmosphere, and depending on the interaction with the different particulates, they are scattered, and the backscatter is received at the sensor, at the satellite sensor, and it estimates the vertical profile of the atmosphere of the aerosols. So it estimates the at different profiles, at different levels of the atmospheric layers, how much is the aerosol concentration, what is the structure of the aerosols, what are the types of aerosols, what are the sizes of aerosols, and it measures on a different temporal resolution. So in the nutshell, if you see the commonly used the Earth observation satellites and the geostationary satellites. So on the left hand side, you can see the Earth observation satellite, which are global in global coverage. So MODIS, it measures every day. So that is every part of the Earth is covered every day. In fact, twice a day. We can say 12 hours a day. One will be at the noon time, that is the afternoon time, and another will be late night time. So around 1:30 in the afternoon and 1:30 at night. So MIs are around 6 to 8 days. We have a temporal resolution that every 6 to 8 days we have a data of a certain area. VIRS, similarly, every day we have ozone monitoring instrument every day. Now Sentinel 5P, that is tropomy data every day. Now in the geostationary platform, here the temporal resolution is very high. So from every 15 minutes or every half an hour we have a data. So those activities or those phenomena which require very high temporal resolution, like for example, if there is a forest fire, we want to see what is the extent of the fire every hour or every 3 hours, what is the spread of the fires. For example, the disaster, for example, a cyclone, or we can see the floods, how it is, covering from or spreading from one area to other area in very fast time in a few hours. So in that we require a high temporal resolution data. In that, geostationary platforms provide the best solution. In terms of pollution also, for example, somewhere it can be every day or it can be every 3 hours. We want to see what is the impact or how the air pollution is spreading from one region to another region. So depending on our objectives, we can choose whether we can choose an Earth observation satellite or a geostationary satellite. So Indian geostationary satellite, INSAT 3D, it provides the best solution as a product of the Aerosol. GOES is a US geostationary satellite. It also provides the Aerosol products. This is the SIVRI is the Meteosat, that is European satellite program, geostationary satellite program, which also provides the Aerosol product on 15-minute scale. Japanese program on Himawari, this is a sensor which also provides similar information every 15 minutes. So in the nutshell, I have given here, this is geostationary, POLA means Earth observation, and this is the spatial resolution. So from the geostationary, that is 36,000 kilometers above the Earth's surface, they provide the aerosol product at 2 kilometer scale, and this is every day and night. This is every 15 minutes. So you have a data every 15 minutes to half an hour, day and night. Himawari 2 kilometers, Meteosat SIVRI 3 kilometers, our INSAT 3D and 3DR. These are two different sensors, but having the same configuration. 4 kilometer resolution, and these are Earth observation. These are around 600 to 700 kilometers, and they provide slightly higher resolution than the geostationary. So this is 1 kilometer. VIRS is 375 meter. These are the details of the INSAT 3D satellite, and this is having 6-band imager. So 1 kilometer in the visible and shortwave infrared, 4 kilometers in middle infrared, thermal infrared, and 8 kilometers in water vapor. So not only it is used for aerosol, because the lecture is on aerosol, that's why this is one of the product, but there are different products. So these sensors not only are useful for the atmospheric aerosol concentration, but also for different products. So if you see the list of the products, so it can be used. These channels can be used. The imager channels can be used. The imager channels can be used to estimate the cloud mask, the outgoing long wave radiation. This also helps to estimate the precipitation, that is the rainfall. It gives a quantitative estimation of the rainfall. Of course, the sea surface temperature, the snow cover, fire, smoke, of course aerosol, the cloud motion vectors, the water vapor, wind vector, the upper tropospheric humidity, fog. So these are the parameters, geophysical parameters, which are used to study, and this can be used in different models to estimate or to understand a particular phenomena. So this is just a glimpse of how the INSAT, our INSAT 3D imager look like, and there is the background is the true color image, and you see the white things. These are the clouds and the snow, and on that I have superimposed the fire points, the thermal anomalies, that is the hotspot, that is the higher temperature as compared to the background. So something is happening, that is there is a fire, and these red dots denotes the active fires that is happening on the ground. So you see that this region, the Middle East region, and then you see the Indian subcontinent and the Southeast Asia, Myanmar, Thailand, and other regions where there are active fires. The fire is happening, forest fires. And on this there is another layer. You see this color. This is the pollution or the aerosol loading. So how that is, these are emitted from certain sources, and not only they stay there, but also it gets transported due to the winds and due to the different profiles, different wind speeds and directions. It moves from one place to another place. And if you want to see the temporal nature, so we can see every 15 minutes, every half an hour, every day, how the things or the pollution levels are spreading from one region to another region. You see every day now, for example, this is one of the day, this is another day. So like this, we can see how the temporal resolution changes and how much loading or how much intensity of the loading is there at one particular place. This is the dust loading, that is the pollution due to the dust, and this is our OceanSat, our Indian satellite OceanSat 2 sensor was used to delineate or to estimate the dust. So you can clearly see that is 11th June, this is 13th June, 15th June, 17th June, how the dusts are transporting from one place to another place. I think. Now the same thing. This earlier slide was from the OceanSat 2, and if you want to see the same phenomena in the INSAT, also we can see how it is moving. You see. So within 2 days, and this is 1 hour, every 1 hour, and 1 hour, how it is moving. So one can see how it is progressing in the last 2 days, how it has progressed. So you can clearly see that it has spread from the western region. It has come from the far west and entered in the Indian landmass in the northern region, and as the time progresses, due to the high winds, this dust also progresses toward in this northern India and particularly over the Indo-Gangetic plain. And now it is very high over the Punjab, Haryana, NCR region and eastern UP, and then slowly it proceeds further and goes to the central Indo-Gangetic plain and to the eastern Indo-Gangetic plain. And if we see at the ground level, if we measure from the CPCB, if you measure the particulate matter concentration is very high, PM10 levels, because these are the dust coarser particles. So you see, for example, in a day, as the time progresses, 5 a.m., 10 a.m., 3 p.m. So every 5 hours, every 3 hours, there is a change. And this also, satellites can also measure. The geostationary satellite can also measure every 15 minutes, every half an hour, or every 1 hour, whatever time interval you require. So the least is every half an hour you get an image, and you can average it out for 3 hours or 1 hour, and one can see what is the concentration pollution level at a particular area. And you see the composite one, the thick uh, uh, smoke or the dust from this pollution level. So we can build up an animation. In the same thing, we can see in the animation. So every half an hour we have an image, and we can see, we can find out, or we can see the level of the concentration, how it proceeds from one place to another place. This can there's a glimpse of that, how we can study how it can be used. So, for example, the seasonal variation we can understand. For example, the northwest Himalayas or the northern India. So, taking a large amount of data, for example, number of years of data, one can also visualize the spatial distribution as well as the intensity, and depending on the different seasons, how the aerosols or the aerosol loading, that is the air pollution loading, is changing from one season to another season, and what is the intensity level. So this is the intensity level from 0 to greater than 1. It means 0 less than 0.2, or this is the clean atmosphere, and here there is a lot of loading. So as the red or brighter red, we see a lot of loadings. So we can, during the winter also there is an emissions because of the biomass burning and other. So this region, Indo-Gangetic Plain, is having a higher aerosol loading. Pre-monsoon season, during the summertime, because of the dust, as we have seen in the last slides, that there is a Sahara dust from the northern Africa. It transports from northern Sahara to the Indian region. Hence, we have much of dust loading or the air pollution loading over the Indo-Gangetic Plain. Now, we can also compare, we can also validate our results from the satellite on the ground. So the ground data, different stations one can take, and we can also cross-check what we are getting from the satellite data and how it is being correlated with or validated with the ground data. Also, we can also associate this with the wind trajectories, that is wind profiles, from where the winds are coming. For example, how do we know that these aerosol loadings or this dust is coming from northern, that is the North Africa Sahara region, from the far west? Because from the air mass trajectories, that is the air masses which are traveling from there to this region, we can see, we can calculate, and then we can justify that this aerosol loading is due to the air masses which are coming from this region. So the air trajectories helps to validate our results. We can have the like, for example, your fire points, that is the actual hotspots from where the fire actually is happening on the ground, and from there you see this is smoke and dust. This white thing is the smoke and dust, how it is traveling, and then you can cultivate different seasons, and this is the estimation of different seasons, and you can build what is the aerosol optical depth or the dust loading over this season, and then you can see the intensity of these regions, how they are changing from one place to another place. Thank you.